Welcome to Neuron.com, where learning medical concepts is as easy as watching cartoons. In this video, we will talk about plasma protein binding. So let's get started. We know that after absorption, the drug is distributed to various compartments of the body, correct? One such thing where the drug goes is within the blood itself. It is plasma proteins. Yes, the plasma proteins serve as a drug reservoir right within the blood. First, let's see the proteins involved in drug binding. First, albumin. As you know from physiology, the most abundant protein in plasma is albumin. Accordingly, here also, albumin is the most important contributor to the drug binding. Acidic drugs mainly bind to albumin. For example, salicylic acid, warfarin, penicillins, sulfonamides, tolbutamide, etc. bind predominantly to albumin. Next, we have alpha-1 acid glycoproteins. While acidic drugs bind to albumin, basic drugs usually bind to alpha-1 acid glycoproteins. For example, propranolol, lidocaine, imipramine, quinidine, prazosin, etc. bind avidly to alpha-1 acid glycoprotein. Apart from these major contributors, there are some miscellaneous proteins too, where the drugs bind. For example, steroids bind to a corticosteroid-binding globulin called transcortin, thyroxine to alpha-globulin, etc. Among all these proteins, albumin is the most abundant. So binding to albumin is quantitatively more important. So these were important proteins. Now let's discuss the characteristics of the binding. First of all, the binding between the free drug and protein is reversible and in a dynamic equilibrium. As the drug concentration increases, the binding also increases. Thus, the fraction of total drug in plasma that is bound is determined by the drug concentration. However, the quantity of proteins in plasma is limited. So at some concentration, all the proteins are saturated, and there won't be any further increase in binding. Beyond that concentration, fractional binding would be less. Now, the extent of binding depends on the individual compound. We cannot make any generalization based on pharmacological or chemical class. Even a small chemical change can markedly alter protein binding. For example, flurazepam, alprazolam, and diazepam all belong to the same class of benzodiazepines, yet they have markedly different plasma protein binding. As you can see here, flurazepam is 10% bound, alprazolam is 70% bound, and diazepam is 90% bound. Thus, binding may vary greatly even among the drugs from the same group. Please note that the generally expressed percentage of binding refers to the binding at the usual therapeutic plasma concentration of the drug. For example, at its usual therapeutic concentration, 70% of the alprazolam is bound to plasma proteins. And one more thing. The generally expressed plasma concentration of a drug refers to both bound and free drug. For example, if someone says the plasma concentration of diazepam is 1 milligram per liter, that means this 1 milligram includes both bound as well as the free drug. So these were the basic features of plasma protein binding. Now let's talk about the clinical significance of this binding. First, being too large in size, the plasma proteins cannot cross the capillary membrane. So along with them, the drug bound to them also remains inside the vessel. So highly plasma protein-bound drugs tend to have a lower volume of distribution. Second, the bound fraction of the drug is not available for action or elimination. Only free drug can bind to its target molecules and produce the action. Protein-bound drug cannot. Similarly, only free drug can cross the capillary wall and be metabolized or excreted. The bound drug is not accessible for elimination. However, as the free drug is eliminated, the bound drug is released from the protein. This drug is now available for action and elimination. Thus, protein binding serves as a storage site for the drug. Our next point is in direct continuation of this one. High protein binding generally makes the drug long-acting. This is because the elimination mechanism cannot access the protein-bound drug, as we saw earlier. For example, in the kidney, the protein-bound drug cannot cross the capillary membrane, so it cannot be excreted. So generally, high protein binding makes the drug longer acting. However, this general rule is not always true. If the drug is actively extracted by the kidney or liver, high plasma protein binding actually speeds up the elimination, making the drug short-acting. For example, here the drug is actively secreted in the renal tubule. So the concentration of the drug in the renal interstitium falls. So the free drug in plasma diffuses out. The resultant fall in concentration of free drug in plasma causes release of the drug from the protein in peritubular capillaries. And now this drug too is eliminated. This way, the bound drug keeps releasing and getting excreted. In a nutshell, high protein binding brings more drug to the kidney, and active extraction pulls this drug out of the protein and eliminates it. This speeds up the elimination, making the drug shorter acting. For example, due to such excretion, the plasma half-life of penicillin is only about 30 minutes. The same applies to the liver also, if the drug is actively extracted by the liver. Please note that in this case, excretion happens only by passive diffusion. There is no active extraction. So the concentration of free drug in plasma does not fall enough to cause a quick release of bound drug. So even though the proteins are bringing more drugs to the kidney, it's not immediately excreted. In summary, high protein binding alone makes a drug long-acting. But if a highly protein-bound drug is eliminated by active extraction, it's excreted faster, so the action becomes shorter. Next, highly plasma protein-bound drugs are difficult to remove by dialysis. Reason is the same. Because of their large size, proteins cannot cross the dialysis membrane, so along with them, the bound drug also remains within the blood. So, in case of poisoning by such a drug, dialysis is not effective. We need to use other special techniques to treat such poisoning. Coming to the next point, diseases may alter drug binding. For example, this figure shows the normal level of protein in plasma and the concentration of free drug at that level. Now compare it with diseases. In case of liver disease, albumin levels are decreased. So the drug binding is reduced, and the concentration of free drug increases at the same dose. On the other hand, in conditions like myocardial infarction, inflammation, etc., acute phase reactant alpha-1 acid glycoprotein increases. This leads to increased binding to this protein. So in such a case, the same dose achieves a lower concentration of free drug. Thus, diseases may alter protein binding. Next point. One drug may bind to more than one site. And conversely, more than one drug may bind to the same site. If two different drugs have affinity for the same site, it gives rise to displacement interactions. So now let's talk about displacement interactions. In this, drug with higher affinity for the protein displaces the one with lower affinity. This increases the concentration of free drug with lower affinity. For example, phenylbutazone and salicylates displace tolbutamide and increase its hypoglycemic effect. Indomethacin and phenytoin displace warfarin and increase its anticoagulant effect. Now, in theory, this sounds very important, but practically, the impact of displacement is usually not that significant. There are multiple reasons for this. One, the released drug gets distributed throughout its volume of distribution. Second, most drugs follow first-order elimination kinetics. So with increased concentration, the rate of elimination also increases. Because of this removal of the drug from the plasma, the new steady-state concentration of free drug is only marginally higher. Thus, the overall impact of displacement is minimal. Moreover, two highly bound drugs do not necessarily displace each other. This happens if they bind to different sites or different proteins. For example, probenecid and indomethacin both bind to albumin, but at different sites, so they do not displace each other. Similarly, acidic drugs mostly bind albumin, and basic drugs mostly bind to alpha-1 acid glycoprotein, so they also generally do not displace each other. For all these reasons, significant drug interactions purely due to displacement are rare. So this was all about plasma protein binding. Before we see the summary, I want to tell you about my website, nonstopneuron.com. It has over 300 animated videos, providing an in-depth explanation of medical concepts. The animations make learning easy, fun, fast, and also give you a longer-lasting memory. The website offers easy navigation and a distraction-free environment for the best learning experience. So I recommend exploring the videos on the website. Now let's have a quick summary. After absorption, the drug gets distributed to various body compartments. One such distribution site is plasma proteins. Albumin is the most important contributor to the drug binding. Free drug and bound drug are in dynamic equilibrium with each other. The percentage of binding depends on the concentration of the drug. The extent of binding depends on the individual compound. We cannot make any generalization based on pharmacological or chemical class. Highly protein-bound drugs tend to have a lower volume of distribution. Only a free drug can produce the action and be eliminated. A protein-bound drug is not available for action or elimination. It serves as a reservoir. High protein binding generally makes the drug long-acting. But if a highly bound drug is actively extracted, the elimination happens faster. A highly protein-bound drug is difficult to remove by dialysis. In some diseases, plasma protein levels are disturbed. This may alter drug binding. If two drugs have affinity for the same binding site, the drug with higher affinity displaces the one with lower affinity. This increases the concentration of the free drug. However, this free drug is distributed to its volume of distribution, and increased concentration usually increases elimination also. So the overall impact of displacement is usually not significant. For watching the video till the end, here is a bonus point for you. The plasma has bound as well as free drug. But during diffusion, the equilibrium happens with the free drug only. The bound drug does not directly participate in diffusion. With a highly protein-bound drug, the concentration of free drug is less, so filtration and consequent excretion is less. And with a low protein-bound drug, the concentration of free drug is high, so the filtration and excretion is more. That's it for this video. If you liked it, please share it with your friends and colleagues too. And don't forget to visit the website, which is the best place to explore my videos. Thanks for watching. See you in the next video.